of the ionization energy. Okay, so before we look at to the trends, okay, in the periodic table, okay, let's look at to the definition of the ionization energies. Okay, we have start, okay, the periodic trend with the electronegativity trends, okay, in which the electronegativity increases across the period, and then it is increases going up the group. Okay, and then the second trend that we discuss is the trend in the atomic size, okay, in which the atomic size is decreases across the period, and then it is increases going down the group. Okay, so this is the third one. Okay, so ionization energy, okay, is defined as the minimum energy that is required to remove the outermost electron from the gaseous atom or ion. Okay, however, this definition is not the complete definition. Okay, we need to have, if we look at the textbook, okay, it is the energy that is required to remove 1 mole of electron from 1 mole of gaseous atom or ion. So we have to have this 1 mole. Okay, if let's say you have to define ionization energy, okay, you have to give the complete definition. Okay, it is the minimum energy that is required to remove 1 mole of electron from 1 mole of the gaseous atom or ion. Okay, and the first electron that we remove from an atom, okay, the first electron that we remove, of course, from an atom. Okay, because we start with the neutral atom. For example, if we have a beryllium, okay, Be has 4 electron. Okay, so Be, the first shell, the second shell, okay, so the 2 electron in the first shell, okay, and then another 2 electron in the second shell. Okay, so the energy that is required to remove the first electron, okay, of course that it will start with the outermost one, okay, the one that have the highest principal quantum numbers. Okay, because it is the one that have a weakest attraction towards the nucleus. Okay, so to remove this electron, okay, from the system of the beryllium, okay, it will require energy. Okay, because each electrons in an atom, okay, are held together in the system of that atom because they are actually having the electrostatic attraction, okay, with the nucleus. Okay, because we have a nuclear charge inside the nucleus. We have a proton there. Okay, so to remove it, okay, it will require energy, and this energy that is required is what we call as the ionization energy. Okay, because the energy need to be supplied, okay, it is actually to overcome the electrostatic attraction that I mentioned just now. Okay, so the first electron that we remove, we call it as the first ionization energy. Okay, if we remove the second electron, okay, that is the second ionization energy. If we remove the third electron, so that is the third ionization energy. So when we remove the first electron, okay, of course that this A, electron A, is being removed from a neutral atom of beryllium. Okay, so if let's say our X here is beryllium gas, so beryllium will turn to Be plus gas with 1 electron removed or come out. Okay, and then the enthalpy change or the energy change here will be positive because the energy is required, it is absorbed by the system. Okay, so that is why, okay, the first ionization energy is always removed from a neutral atom. Okay, however, if we remove the second electron, electron B, okay, it is being removed from the Be plus. Okay, after we have removed the first one, we want to remove the second electron. This second electron is actually being removed from the Be plus ion. Okay, so that when we remove the second electron, Be will turn to Be2 plus ion. Okay, with the second electron come out. Okay, delta H positive. Okay, so if you got a question, define ionization energy in general. So your answer will be, it is the minimum energy that is required to remove 1 mole of electron from 1 mole of gaseous atom or ion. Okay, because it is general. However, if we talk about the first ionization energy, okay, it means that the first electron that is being removed is always removed from 1 mole of the gaseous atom. Okay, no ion. Okay, it is not ion because the first electron is always from atom. Okay, we remove the second, the third, and the fourth. Yes, they are coming from the ion. Okay, so be careful. Look at to the question. Carefully, it's either general ionization energy or first ionization energy. But if let's say the question asks you to define third ionization energy. Okay, third ionization energy is the energy that is required to remove this third electron. Okay, C. Okay, so if we want to remove C, it is also being removed from 1 mole of the gases ion. Okay, at that time we remove the C from Be2 plus. Be2 plus gas, so that it will turns to Be3 plus gas plus 1 electron come up. Okay, so this equation represent the first ionization energy. This is the second ionization energy, and this is the third ionization energy required. Okay, sometimes the question we told you to write the fifth ionization energy of certain species. Okay, if let's say I want you to write the fifth ionization energy of magnesium. Okay, so what happened is when it is the fifth ionization energy means that it is the fifth electron come up, so that it will form Mg5 plus gas. Okay, so that this Mg5 plus gas is actually coming from Mg4 plus gas. Okay, and then 1 electron come out. Okay, delta H IE5. This is the fifth ionization energy. Okay, so if it is the fifth one, it will form 5 plus. If it is the first IE, it will produce 1 plus. If it is the second IE, it will produce 2 plus ion. If it is the third IE, it will produce the 3 plus ion. Okay, look at to focus on the product. Okay. So this is another example on magnesium. Okay, magnesium turns to Mg plus. Okay, it produces the positive 1 ion. So we know that this is the first ionization energy. Okay, and the value, the enthalpy change is 736 kilojoule per mole. Means that if we want to remove 1 mole of this electron, it required 736 kilojoule energy. And then we remove the second electron. Okay, means that this is the second ionization energy. How do we know that this is the second ionization energy? Look at to the product that is formed. It is forming Mg2 plus ion. Okay, so this is the second IE. Then the energy is 800 kilojoule per mole. Means that to remove 1 mole of this electron, then it required 1.8 1800 kilojoule energy. Okay, and this process is endothermic. Okay, you have to remember this. Okay, the process of removing the electron are endothermic process, okay, in which the energy need to be absorbed by the system. So the surrounding need to supply the energy. Okay, so we have to supply the energy so that the system of the atom or ion absorb it. Okay, it is because the energy is required to overcome the electrostatic attraction between the electrons, okay, and the nucleus. Okay, so if we have a metal atom, okay, for the metal atom, they tends to lose electron, okay, so that they will gain the electronic configuration of the noble gas. Okay, if we have a metal of sodium, okay, so it tends to Na plus. Okay, because the sodium will achieve the noble gas configuration when it is achieving positive 1 ion, because Na configuration is 1s2, 2s2, 2p6, 3s1. So when it turns to Na plus, the configuration will be 1s2, 2s2, 2p6. Okay, so the sodium will release or will lose one electron so that it will achieve a noble gas configuration, and this is a stable configuration for ion. Okay, so when we talk about trend, okay, we want to relate the ionization energy with the trend in the periodic table. So the trend of the ionization energy of different elements, okay, in the periodic table is actually also related to the ZEF. Okay, it is because we know that the ZEF is the net charge, okay, that is felt by the valence electron towards the nucleus. Okay, the value of ZEF will determine how strong the attraction between the electrons, okay, the valence electron with its nucleus. So of course that if we have a high ZEF value, okay, when the ZEF is high, we know that the attraction is strong. Okay, when the attraction is strong, means that it is harder to remove. Okay, so when it is harder to remove, means that it will require more energy. So when it require more energy, okay, so the ionization energy will be greater. Okay, so this is the relationship between ZEF and also the ionization energy. Okay, so when ZEF increases, okay, if the effective nuclear charge increases, it requires more energy to remove the electron, okay, and the ionization energy will be high. So basically, the trend of the ionization energy is opposite to the trend of the size. Okay, if we have a smaller size, okay, it is actually due to the stronger attraction between the valence electron and the nucleus. So the smaller size will have a stronger attraction between valence electron and nucleus. So it is harder to remove the electron and it requires more energy as compared to if we have a big size atom, okay, means that the valence electron further from the nucleus. So they have a weaker attraction with the nucleus. So it is easier to remove them and the ionization energy will be lower. Okay, so the trend of the ionization energy, this is a trend we focus when we talk about trend, we're just focusing on the first ionization energy. Okay, of different element. Okay, we are not differentiate. Okay, we are not comparing the first, second, third IE of the magnesium with the first, second, third IE of beryllium. Okay, we're just comparing their first IE. Okay, the first ionization energy of different elements. Okay, so basically these are the trend. Okay, as I said just now, the first ionization energy increases across the period and it is also increases up the group. Okay, why? Because the size decreases across period. Okay, and then the size increases going up the group. Okay, or this, sorry, the size increases going down the group. Okay, so the trend are opposite. Okay, so this is the trend of the first ionization energy. So generally we know that, okay, the size of the lithium, okay, in a period 2 elements, okay, lithium is the biggest, followed by beryllium, boron, carbon, nitrogen, oxygen, fluorine. Fluorine is the smallest. Okay, so we know that the fluorine will have a higher ZEF compared to lithium until fluorine. So it have a higher ZEF, it will have a higher first ionization energy. Okay, it is the smallest one, highest ZEF, highest first IE. Okay, compare for the group. Okay, going down a group, we know that the size increases. Okay, so when the size increases going down a group, the first ionization energy decreases going down the group, or the first ionization energy will increase going up the group. Okay, you just remember about the size. Okay, the smaller the size, the higher the first IE. The bigger the size, the lower the first IE. Hmm. Okay, so look at to the figure. Okay, the first period, hydrogen and helium. We know that helium is smaller than hydrogen. Look at to the first ionization energy. Okay, the first ionization energy of helium is higher than hydrogen. Okay, look at to lithium to neon. Okay, we know that the size decreases from lithium to neon. Then we observe that the first ionization energy increases from lithium to neon. Okay, the size decreases from potassium to argon of the period 3. Okay, then we observe that the first ionization energy increases across the period. Okay, if you look at to the group 1 element, okay, lithium, sodium, potassium, rubidium, cesium, we observe that the trend decreases. Okay, because lithium is the smallest one, cesium is the biggest. Okay, so the bigger the size, the lower the first ionization energy. Okay, so if we zoom in to the period 2 and period 3 elements, okay, we will observe there are some spots, okay, that are having anomalies or irregularities, that shown irregularities there. Okay, if we zoom in, okay, we have a lithium to neon. Generally, it follow the trend which is increases across the period 2. Okay, same goes with the period 3, increases from sodium to argon. Okay, however, we observe that there is a different the irregularities here. Okay, between magnesium, aluminium, phosphorus, sulfur, okay, beryllium, boron, and also nitrogen, oxygen. Okay, or if we look at in terms of figure, okay, number, okay, lithium 500. Okay, it is increased to 9, 8, 1000, 13, 16, 2000. Okay, general follow general trend, increases across the period. Okay, however, here we observe that okay, it's supposed to be beryllium have a lower first ionization energy than boron because boron is smaller in size. Okay, so we know that the smaller the size, the stronger the attraction, the more energy required to remove the electron, right? Okay, however, we have to be able to explain why, even though the size of the beryllium is bigger than boron, why it have a higher first IE. Okay, or opposite to that, vice versa. If the boron, okay, we are focusing on boron, why, even though the size of the boron is smaller than beryllium, but it has a lower first ionization energy. Okay, so these two pair, okay, and these two, okay, between nitrogen, oxygen. Okay, we know that oxygen is more to the right of the periodic table. It is group 16, so that the size of oxygen is smaller than nitrogen. Okay, however, even though it is smaller, the first IE is lower than the first IE of nitrogen. Okay, so let's look at to the further explanation on this. Okay, we are comparing the first set, okay, that having irregularities, which is between beryllium and nitrogen. Okay, so beryllium is found to have a higher first ionization energy than boron. Okay, and then nitrogen have a higher ionization energy than oxygen. Okay, so this irregularities is actually due to the stability of the half-filled and completely filled orbitals. Okay, remember we have discussed on the configuration last time. Okay, when we have a extra stability, when the configuration is either half-filled or completely filled or full-filled configuration. Okay, so let's look at to the beryllium. Okay, when we write the configuration of the beryllium, we observe that the configuration of the beryllium that have 4 electrons is 1s2, 2s2. Okay, so we have a full field orbital of 2s here. Okay, as compared to in the configuration of the boron, okay, it has 5 electrons. So the configuration is 1s2, 2s2, 2p1. Okay, in which the last electron or the first electron that will be removed from the boron is this electron. Okay, and this electron come from 2p orbital that is unfilled, or it is a partially filled orbital. Okay, so to remove the first electron of the beryllium that come from partially filled orbital that have no extra stability, of course that it is easier as compared to if we want to remove this electron, okay, from the beryllium, that is the first electron that we remove from beryllium. Okay, so we disturb the stability of the full filled orbital of 2s if we remove it. So that it will require, it is harder, right? Okay, and that is why it require more energy to remove it. Okay, so due to that, okay, even though the size of the boron is smaller than the beryllium, okay, due to the first electron that is being removed from boron come from unstable partially filled orbital of 2p. So it is easier to remove this electron and require less energy as compared to the first electron that we remove from beryllium, okay, that come from a stable, completely filled or full filled orbital of 2s. Okay, so it is harder to remove the electron and it require more energy. Okay, therefore the first IE of Be is higher than the first IE of boron. Okay, that's how you answer it. Okay, and if you look at to the set, the second set, which is the nitrogen and oxygen. Okay, so nitrogen's configuration is 1s2, 2s2, 2p3. Okay, and the configuration of the nitrogen, okay, lasts with the 2p3, in which this is the half-filled orbital. Okay, half-filled configuration that have extra stability. Okay, as compared to, okay, when we have oxygen, the configuration lasts with 2p4, okay, in which this configuration is unstable configuration because it is a partially filled or unfilled configuration. Okay, so how to explain this? Okay, this is the first electron that is removed because we are comparing the first IE. Okay, so it means that the energy that is required to remove the first electron, in which this is the first one. Okay, as for the oxygen, the first electron that is being removed is this electron. Okay, the second electron in 2p orbital. Okay, so if we remove this electron, okay, that come from a stable of 2p orbitals, so that it is harder and require more energy. Then how should we write the answer, the explanation? Okay, so you can start with the first electron removed from nitrogen come from a stable half-filled orbital of 2p. Harder to remove the electron, require more energy. Okay. And then you explain about the oxygen. Okay, the first electron removed. Okay, ni first remove from oxygen come from unstable, unfilled orbital of 2p. Okay. Actually, there is extra points. Okay, why this electron is easier to be removed? Because we observe that that this electron is actually being paired in the same orbital. Okay, when we have two electrons in the same orbital, of course that it will experience a stronger electron-electron repulsion. Okay, because we have two negative species in the same orbital, in the same room. We said that orbital is like a room, right? Okay, we have two negative species that always repel each other in the same orbital. So this electron will experience a stronger or more electron-electron repulsion. Of course that it is easier to remove it. Okay, that is the second reason. Okay, the first one because it is come from unstable, unfilled orbitals. The second reason is because the electron being paired in the same orbital of 2p. So it experience stronger electron-electron repulsion. So easier to remove, require less energy. Okay, you have to have all this explanation. Okay, if let's say you have to explain on this phenomenon, on these irregularities. Okay, nitrogen and oxygen. So it is the same as what is happened, okay, in the period 3. Okay, just now beryllium, boron, nitrogen, oxygen, they come from period 2. Okay, and then the same trend that is happened in the period 3 below that 4 elements just now. Okay, between magnesium, aluminium, group 12 and group 13, phosphorus and group 2 and group 13, phosphorus is group 15 and sulfur group 16. Okay, so we observe that if we have to explain about magnesium and aluminium, okay, this is the first electron removed from magnesium. Okay, it comes from a stable full field orbitals of 3s as compared to the first electron removed from aluminium is this electron that comes from unstable unfilled orbital of 3p. Okay, so it is harder to remove this electron, okay, and require more energy. It is easier to remove this electron, require less energy. That is why the first ionization energy of the magnesium is higher than the first ionization energy of aluminium. Okay, if we look at to the phosphorus and sulfur, okay, the first electron removed from phosphorus come from a stable half-filled orbital of 3p. So it is harder to remove the electron and require more energy as compared to the first electron removed in sulfur come from unstable partially filled orbitals of 3p, and then the electron being paired in the same orbital, so it experiences a stronger electron-electron repulsion. Okay, therefore, it is easier to remove the electron and require less energy. Okay, any question?
No, madam.
No, madam.
No, madam.
Okay, so that is actually on the periodic trend, okay, on the first ionization energy of different elements. Okay, now we want to move to the second part under this ionization energy subtopic, okay, which is determination of the electronic configuration by using successive ionization energy value. This time we are focusing on the element one by one. Okay, we don't compare between different elements. Okay, this is the difference in the ionization energy of the first electron, the second electron, the fourth, and so on electron that we remove from the atom. Okay, so this table 8.2, Okay, we have a element of hydrogen. Okay, this is the first ionization energy of hydrogen. Means that the energy that is required to remove that electron in hydrogen. And then helium, first IE, second IE. Lithium, until the third IE. Okay, now the question, why lithium only have until third IE? Why there is no fourth, fifth, and sixth? As compared to calcium here, it have first, second, third, fourth, fifth, sixth.
Only 3
Okay, why there is
electrons.
no value? Yes,
Only
because
3 electrons.
lithium only has 3 electrons. Means that the maximum number of electrons that can be removed is 3. Same goes with the hydrogen. We stop at the first IE, no value second, third, fourth, because hydrogen only has 1 electron that can be removed. Okay, so this is what we call as the successive ionization energy. Okay, how much energy that is required to remove the electrons from each elements. Okay, if we focus on the neon, for example, okay, element number 10, the first IE is 2000, third is 3009, the fourth is 6001, the third is 6001, the fourth is 9003, fifth 12,000, and the sixth IE is 15,000. Okay, energy, kilojoule energy. Okay, zoom in, focus on the hydrogen to nitrogen only. Okay, when we study their successive ionization energy, then we actually can observe there are trends here. Okay, what is happening between this star is actually we observe that at the lithium. Okay, focus on lithium first. Okay, after the 500, it is turns to 7,000. Okay, for beryllium, okay, the first IE 800, the second is 1,007. Suddenly, the third one is 14,000. Okay, you should know that. Okay, the successive ionization energy will keep on increase. Okay, it will increase. Okay, from the first and then the second, the third, the fourth, the value or the energy that is required is getting higher. Okay, means that the subsequent electron being removed is more harder. That is why the energy need to be supplied more. Okay, however, we observe that yes, we accept that they have to be increased. Okay, because the subsequent electron is being removed will have a stronger attraction with the nucleus. Okay, however, why there is a significant difference between this value? Okay, for carbon, for example, 1000, okay, this is supposed to be 2000, okay, no 3. Okay, 2522. Okay, and then 4000, then 6000 here. Suddenly it jumped to 37,000. Okay, here is 1000 for 2008, 4.5k, 7.4k, 9.4k. Suddenly it is turns to 53k, and then it is increased to 64. Okay, the big jump is happened here. Okay, so actually from this successive ionization energy, we can determine how much valence electron that we have in that specific element. Okay, and in general, okay, the successive ionization energy always increase. This is what I said just now, because each subsequent electron is being pulled away from an increasingly more positive ion. Okay, so it require more energy. As example that is given here, if we remove the first electron of the magnesium, it is being removed from Mg neutral. But if we remove the second electron in the second IE, it is removed from positive 1 ion. If we remove the third electron, it is from positive 2. The fourth electron from positive 3. So the charge of that positive ion keep on increase. So it is harder to remove the subsequent electron. Okay. Um, this is the example. Okay, if we look at to this figure, the 3 ionization energy of the beryllium, this is the first IE 0.9. The second IE, it is increased to 1.7. Suddenly, the third IE, okay, there is a big jump there to 14.85 energy. Okay, so the question is why there is a significant difference here, much different, or we call it as the big jump there. Okay, so it is actually, okay, this jump is appear, okay, after the outer electron or after all the valence electron has been removed. Okay, means that the electron, the next electron that is removed is being removed from the inner or core electron. Okay, if we come back to this beryllium, okay, we know that the beryllium has 4 electrons. So Be, this is the first shell and the second shell. So this is the first electron, sorry, this is the first electron, the second electron, this is the third one, and the fourth one. Okay, so the first electron that is removed is this A, B, C, and D. So the first electron removed is A. Okay, if we write the equation to show the first ionization energy of beryllium, it is Be, gas turns to Be plus gas plus 1 electron. Okay, delta H, IE 1. Okay, so this electron, okay, is actually A. Okay, and then we remove the second electron. Okay, it is actually from the beryllium plus, okay, Be plus gas turns to Be2 plus gas plus the second electron. And this electron is actually B. Okay, after we have removed A and B, okay, means that we don't have this n equal to 2 anymore. We don't have this this outer shell. Okay, so no more. Okay, then we'll observe that we start to remove C and D from the inner shell, which is much closer to the nucleus. Okay, that is why there is a very significant difference. Okay, after we remove the first 2 electron. Okay, so to remove C, okay, to remove this C, okay, it require this amount of energy. Okay, that is why there is a big jump here. It is actually, we have finished, remove all the valence electron. Now this energy is needed to remove the core electron or inner electrons. Okay, that is why there is a big jump there. Okay, so from this successive ionization energy, if we look at to the oxygen, okay, 1.3, 3.4, 5.3, 7.4, 10, 13, suddenly it is 71. Big jump here. Okay, between the 6 and the 7 ionization energy. So we know that the valence electron that the oxygen has is 6 valence electron. Okay, the 7 ionization energy, which is this 71.33, these are the energy that is required to remove the first inner electron, the first core electron. Okay, so it has 6 ionization energy. Okay, so let's look at to the example of the question. Okay, these are 5 successive ionization energy for M, atom of M. Okay, so first question, determine the electronic configuration of the valence electron of M. Okay, before that, okay, if you got a question on this successive ionization energy, it is just involve main block element, which are S and P block. Okay, we do not cover the successive ionization energy for the D block element. It is just for S, group 1, group 2, and group 13 until 18. Okay, so if we want to write the configuration of the valence electron of M, we have to know how many valence electron that it has. Okay, so to know how many valence electron that it has, okay, we look at to the successive ionization energy. We observe that the first IE is 800. Second, 1.5. The third is 3.2K. The fourth one is 4.36. The fifth one is 16K. Okay, so obviously that the big jump is here between the fourth and the fifth ionization energy. Okay, when the big jump is between fourth and fifth means that the fifth electron is actually the inner electron or the core electron. And if the fifth is the first core electron means that this element of M have 4 valence electron. Okay, so when it has 4 valence electron, okay, it has 4 valence electron, so it comes from which group? Group 1, group 2, 13, 14, 15, 18, which one?
4.
14.
madam.
Yes, group 14. Why not group 4? Because I told you that we do not cover
14.
transition element.
B.
Okay, it is just group 1, 2, 13, 14 until 18. Okay, so when it has 4 valence electron means that this element comes from group 14. So when it comes from group 14, so what is the valence electron configuration? The configuration of the valence electron, the configuration of these 4 electron. Remember the general configuration of the valence electron for the group 14? It will be Ns2, Np2. For p block element, the valence electron included the electron in s orbital. Okay, so the configuration is Ns2, Np2. Okay, however, if the question mentioned to you this M located in which period, okay, then you have to write the correct N value. Okay, but since that this M has no information about the period of this M, so we just write the general configuration and use the N value. You cannot simply put 2S2, 2P2 or 5S2, 5P2. You cannot simply put the N value unless the question mentioned to you that it comes from which period. Okay, so we just write the general configuration and then the group number is group 14. Okay, let's look at another example, but before that, okay, this is the second method. Okay, if let's say when we look at to the value, we can observe, we are not sure where is the big jump. Okay, so if we are not sure, sometimes okay, they are questioned when the value they are, it seems like they are 2 jumps. Okay, so how to solve that if you are not sure? Then we have to calculate the ratio. Okay, the IE ratio. Okay, so the second IE divide with the first IE. Okay, this is the ratio between second and first. Then calculate the value. Okay, and then you divide the third ionization energy with the second one. Then we got 2.04. And then you divide, okay, or calculate the ratio between the fourth and the third. Then we got 1.34. And then calculate the ratio between fifth and fourth. We got 3.67. So those that have the highest ratio of the ionization energy, and then okay, the valence electron is between, the valence electron is 4. Means that the big jump is between fourth and fifth. Okay. Okay. The second example, these are the 5 successive ionization energy of A. Okay, study the value. Nur Irdina. Nur Idrina? Idrina, where's your big jump here from this data? Okay, the big jump is observed, okay, between the third and the fourth ionization energy. Correct? Okay, we have 500, 1.8K, 2.7K. Suddenly it jumps to 11.6K. And then 15,000. So the big jump is here. It means that, okay, this element of A has 3 valence electron. Okay, so when it has 3 valence electron, then Sophia.
Yes,
Sophia?
madam.
Okay, this element comes from which group?
Group 13.
Yes, it is group 13. And what is the configuration of the valence electron when it comes from group 13?
NS2 NP2.
NS2, NP2.
Mm.
2 plus 2, 4.
Mm,
It has 3 valence electron.
NS2 NP1.
Okay, it is NS2, NP1. Okay, correct. Thank you. Another example, this is the atom of X. We have 4 successive ionization energy. Study the data. Amirul Ashraf.
Yes, madam.
Okay, so where's your big jump here?
From the second to third ionization.
Okay, the big jump is observed between the second and the third ionization energy. So how many valence electron that the X has?
2.
It has 2 valence electron. Okay, so what is the group number of this X?
2.
Okay, it comes from group 2. Okay, what is the complete configuration if X belongs to the second period? Okay, before the complete configuration, what is the valence electron configuration if it is belongs to second period? You said that it is group 2, right? So what is the configuration of the valence electron?
NS2.
Okay, and S2, but the question mentioned it is come from second period, so you cannot put it as N. The valence electron configuration will be
2s2.
2s2. Okay, and then the question asks us to write the complete configuration, means that we have to start with 1s. Okay, so the complete configuration will be 1s2, 2s2. Okay. Finish with the ionization energy. Okay, let's look at to the workbook. Okay, look at to workbook, question 14. Okay, just now, okay, all the examples that we have discussed just now is when we have a value. Okay, the value. Okay, however, in this question 14, okay, it is not the value that is given. Okay, but the successive ionization energy, okay, is given in a form of this graph. Okay, so the graph of the successive ionization energy value, okay, the energy versus with the number of electron removed. Okay, this is the energy when the first electron removed. This is the energy when the second electron removed. This is the energy when the third electron removed. We observe that it is increases. Okay. However, okay, we know that they are supposed to increase. However, we observe that there is a big jump here between the third and the fourth ionization energy. Okay, when there is a big jump between third and fourth, we know that these three electrons are the valence electron of the W. Okay, so you should be able to identify the group number. You should be able to write the configuration of the valence electron. Okay, and also the complete configuration, since that the question told you that this W is in period 3. Okay, so this is another example. Okay, so I want you to answer this question. Okay, after this. Okay, let us proceed to the last subtopic. Okay, to the last subtopic under periodic trend. Okay, which is the electron affinity. Okay, so electron affinity is defined as the energy that is released or absorbed when 1 mole of electron is added to 1 mole of the gaseous atom or ion. Okay, if you look at to this definition, it is actually exactly the opposite process of the ionization energy. Okay, the ionization energy just now is the energy that is required to remove the electron. Okay, as for the electron affinity, it is the energy that is changes. Okay, it's either release or absorb. Okay, that is why it's either you are using energy release or absorb, or you also can define it as the energy change. Okay, when 1 mole of electron is added to 1 mole of gases, atom or ion. Okay, you can decide you want to use release or absorb, or for me, I prefer to use the energy change. It is general, endothermic or exothermic. Okay, both covered when we are using the term change. Okay, but the process is opposite to the ionization energy, and the value of the electron affinity measures the ability of the atom or ion to receive or gain electron. Okay, measure the ability means that the easier for the atoms or the easier for the ion to receive the electron or to gain the electron, then the more energy will be released, okay, by the system. Okay, the more energy that will be released means that the more negative the value. Okay, because we know that if the energy or the enthalpy is positive, means that it is the endothermic reaction. Okay, the process that required energy. But if the enthalpy or the energy is negative, means that this process release energy to the surrounding or exothermic process. So the easier for that atom or species to receive the electron, then the higher the negative value, means that the more energy that will be released. Okay, that is if we comparing the value of the electron affinity. Okay, so example here, okay, that is given is the bromine when bromine receive electron. Okay, so the equation to choose the first electron affinity of bromine is bromine gas. Okay, the state is compulsory. Okay, bromine gas plus 1 electron so that it will turns to bromide gas. Okay, delta H. Okay, this is the first EA1. Okay, it is different from this EA. This EA is the activation energy. Okay. If we talk about ionization energy just now, okay, it is when the electron removed. For the first ionization energy of bromine is when bromine turns to Br. Is when bromine turns to Br. Br what class?
Minus.
Br.
Plus.
Br plus ion. Because it release one electron. Okay. Then the delta H will be IE1. Okay. But for the electron affinity, it is bromine receive electron. So that it turns to anion. Ionization energy, atom turns to cation. Okay. But in all changes that is happened, there will be energy that is changed. You will learn this in Chem 2 later, the thermochemistry. Any changes that is happened physically or chemically, physical state change or they are chemically changed, they are reactant, there must be the energy that is changes during the process. Okay, it's either it is positive or negative, endothermic or exothermic. Okay, same goes with this. Bromine tends to be R minus, then they involve energy change. Bromine tends to be R plus, also involve energy change, or to be specific, this is IE and this is EE. Okay, so the EA is not the same as the difference between EA and IE is always positive. To remove the electron, energy is always required. It is always endothermic process. But for the EA, it's either exothermic or endothermic. Exothermic when the system release heat, it is negative. Okay, endothermic when the system absorb heat. Okay, so if let's say that element is hard to receive the electron. Okay, example, if we look at to the textbook, can someone search the figure on the electron affinity value? Look at to electron affinity, what page?
Madam, is it 351?
Yes, correct. Page 151. Okay, figure 8.19. Okay, please look at to that figure 8.19. Okay, look at to period 2 elements. We have lithium until neon, right? Okay, I've known that slide. Okay, in here, so I can't share with you. So you have to look at to the textbook. We have lithium is negative 59. Okay, boron negative 26. Okay, and then carbon negative 122. Okay, so the more negative the value, okay, means that the more energy that is released when they receive electron. Then the more energy that the system release means that the easier for that atom to receive the electron. Or so we can say that they love to receive the electron. Then they will release more energy. But if it is hard for them to receive the electron, then it will be endothermic reaction. Energy need to be supplied. Okay, or the system need to absorb the energy. Example is in neon. Okay, if we look at to the neon electron affinity, it is not negative, means that the energy is not being released during the addition of the electron. It means that the neon don't like, or it is not the neon don't want to receive the electron. Okay, but if we still want to form an E negative, okay, then the energy need to be supplied and the neon need to absorb energy. That is why the EE of neon is positive 29. Okay, so why the neon has the endothermic reaction to receive the electron? Okay, because we know that the neon is already achieving the stable configuration, which is 1s2, 2s2, 2p, 6. A full field orbital of 2p. Okay, so if one electron being added to neon means that we will disturb the stability of this configuration and it will make neon turns to Ne minus with the configuration of 1s2, 2s2, 2p6, 3s1. Okay, in which this configuration is less stable or it is not as stable as when the neon achieving full field orbitals of 2p. So when we disturb the stability of the atom that is already stable, so of course that okay, the energy need to be supplied, neon need to absorb energy, then the process will be endothermic process. Okay, that is if we compare the first IE between different elements. Okay, we don't need to memorize the general trend, either it is increases or decreases across the period on the electron affinity. But what you need to know is the more easier the electron, okay, to be added by that element, then the more energy it will release. Means that the greater the negative value, but the harder for that atom to receive the electron, then it will be more positive, okay, or more endothermic reaction. Okay, so this is example of the first electron affinity of the fluorine. Okay, if you have to define first electron affinity, okay, it is the same as ionization energy. Just now, it is the energy change when 1 mole of electron is added to 1 mole of gases atom. Okay, no ion there because it is specific to the first EA. Okay, and the first EA usually negative, usually, okay, but for certain element it is positive. And the more negative the value means that the greater the case of formation of an ion. This is what I said just now. Okay, the easier for that atoms to receive the electron. Okay, so example, if F gas plus 1 electron turns to F minus gas, okay, the EA is 348 kilojoule. Means that 348 energy released because it is negative. As for the second electron affinity, it is defined as energy absorbed. Okay, when 1 mole of electron is added to 1 mole of the gaseous atom or ion. Okay, it is defined as the energy that is absorbed. Okay, why? Because the second electron that is added to the system, okay, will always require energy. Okay, why it is always required energy, or why the second electron affinity is always endothermic reaction? Okay, this is because the electron is being added to the negative ion or anion. Okay, so the strong repulsion felt, okay, oxygen is negative species. This electron is also negative species. Okay, so they will repel each other. Okay, so when this repulsion happen, means that the energy need to be absorbed. Okay, to overcome this electrostatic repulsion between the electron and the negative anion. Okay, so this is the reason why, okay, the second electron affinity is always positive. It is always endothermic reaction. Okay, because the electron is negative, oxygen also negative species. Okay, it is O minus, so that the repulsion happens. So energy need to be absorbed to overcome the repulsion.